Here we are back again in our discussion of sorting and grouping in relational database systems. This is chapter 11 of the DB2 course. If you have a closer look at where the innovation currently happens in the implementation of the PostgreSQL database kernel, then you will see that quite some focus and quite some work is being invested in the parallelization of query evaluation. Parallelism has been no topic in this particular course until now, and it won't pop up in any interesting detail in the rest of this course. It's just a topic that we leave to the side because there is so many other stuff on our plates that we are busy until the end of the course. But in this particular context, in the context of grouping, let's change that for the next few minutes and have indeed, let us have indeed a closer look at the parallel evaluation of grouping and aggregation. These are operations that lend themselves to a very efficient, straightforward, and elegant way of parallelizing them. And it cannot hurt to get an impression of what parallelization can mean during query evaluation. Okay. So how parallelism is exploited by database systems is by spawning a series of workers, series of independent workers that all contribute to the evaluation of a single query. So we are talking about the evaluation of one query here, not about the parallel evaluation of many queries. This is, of course, another option to exploit concurrency, but this is not what we are talking about. We are talking about a number of workers that contribute to the evaluation of one single query. Each of these workers is to be executed in parallel, okay? Maybe each on a dedicated CPU core, or if you have a distributed parallel database system, then each of the parallel instances of your database system could all work together to arrive at the solution or the result of a particular query in an efficient way. Of course, we would constrain the maximum number of these workers to fit the host, to fit the number of computing resources, for example, the number of independent cores that your CPU can provide. So we will benefit the most if all of the workers are busy in an even fashion. And idle workers are no good. So let's try to keep all of these workers busy in an even fashion. All right. One of the workers will be elected to be the leader, to be the coordinator that once all the workers have provided their partial result, will gather these partial results and try to finalize them, merge them, somehow post-process them to produce the final result from all of these partial contributions that the workers can deliver. Okay, so this is, a very general description of parallel query evaluation inside a database system. Let's make this more concrete when it comes to the evaluation of grouping and aggregation. And for that, we will simply switch back to our probe query, the query that was executed over the grouped table. And we grouped the rows of this table by column G. So I brought an instance, a mini instance of that group table with me. We will group by this grouping criterion by column G here. And once we've done that, inside each group, we will perform a summation by column A. So that would be the aggregation that is being performed. The whole parallel evaluation would start by splitting the rows of the input table in an even fashion. All right, so on this slide, the degree of parallelism will be 2. So there will only be 2 workers that are contributing to the evaluation of our queries. So we will split the input table, the load of rows that we have to process, into 2 even batches of rows. This is performed by horizontal partitioning, and this is a batch of 7 rows to process. We cannot evenly divide that, but this could be a split that is almost even. So we would assign these rows to one worker, the worker below here, and these rows, this partition, to the worker that is operating above here. From then on, there will be parallel evaluation. We will perform a parallel sequential scan in both workers, for example. All right, you know that sequential scan can do some post-processing or some processing for us. For example, the evaluation, the interpretation of predicates, or the early evaluation of arithmetic expressions. All of these efforts would be divided evenly between the two contributing workers here. Each of these would perform the scan of the rows in parallel, and we would end up with these two partitions of rows that are handled by the two workers. There is no predicate or other arithmetics to evaluate here, so we would just end up with these two partitions of rows that we have already indicated here by this dividing line. Inside these workers, we would then try to perform the grouping and the aggregation. All right, of course, the focus of each worker will only be on the subset of rows that it has been assigned to operate on. Okay, so there will be two such hash aggregate operations, for example, be evaluated in parallel, and both hash aggregate will build their individual separate hashing tables. All right, so we would end up with two hash tables, and well, we would use the grouping column G as the input to the hash function. From that hash function, we would receive keys. According to these keys, we would place entries in these tables into hash buckets, and you can see that there is the group for the G value 42. Let me focus a bit more here. Well, entries for the group with G value 42 are to be found in this particular hash table, and they are found here in this particular hash table. Other entries might be only occurring in one particular hash table. So G11 and G38, they are only found in these separate entries, but there might be entries in our hash tables that agree on their key value and that agree on their grouping value. All right. So what we compute here are indeed only partial aggregates. We are performing some aggregation, so there's only one 42 value that will contribute to this partial sum, but there are two values in the 42 group that will contribute to this partial sum of 5, which is 1 plus 4. Okay, so what's clear is that when we gather all these partial results, there is some finalization of the aggregation computation to be done. Well, some of the groups here, some of the hash bucket entries may just be reproduced verbatim in the finalized result, and this is true for the group with G38 and G11, and you find these unaltered, unchanged here in the result. But some of the groups may receive entries from all of the contributing workers. And when we've gathered all these partial results, it's our task in the aggregate finalization to in this case add the 5 and the 6 here. This would be the finalization operation that is associated with the sum aggregate. The addition of partial aggregate values will lead to the global aggregate value of 11 here. Each of the aggregates that SQL supports, so sum of course, but also max, min, average, the Boolean aggregates like bool and or bool or, all of these will have their individual finalization operations that can collect partial results, gather them, and then produce a global result here. And well, this sketch of a parallel query evaluation plan is indeed almost directly found when you use the explain on this grouping query and have not disabled all the parallelization features inside PostgreSQL. So the plans that I've shown you until now in this course have all been produced while I had parallelization features of PostgreSQL completely switched off. If you switch on, which would be the default, if you switch on these parallelization features, then what you will see as the plan for this grouping query is the following. Okay, again, we would of course read the plan bottom up or from the inside out. And indeed, it would start with a parallel sequential scan. So a split, an even split of the rows of the grouped table into partitions of even size that are all processed by separate workers. Right? All of these workers would then perform partial hash aggregation or partial aggregation in general, of course by the grouping key G here, which is our grouping criterion. Okay, this would lead to a number of separate hash tables that have been produced. In these hash tables, we will in general find partial aggregate values. Those would all be gathered by the coordinating worker. So as you can see in the plans, we will have a look at these plans over on the terminal, where you see that there will be many more details to be found. But here in this excerpt, you can see that this plan has been performed in a parallelism degree of 3. We have the coordinator, the gatherer, which will collect the partial results once they are available. The gatherer itself, the coordinator itself, the leader itself will also perform partial aggregation, for example, and partial scanning. So there is a parallelism of degree of 3 here. The coordinator, the leader, plus 2 workers that have been spawned. Once all the partial results, the partial hash tables in this case, have been gathered, well, there's now the final task of finalizing these hash aggregates. In the case of summation, as we've already discussed, it would be now time to sum all the individual contributions to form the global sum aggregate value. All right. So that's a quite literal implementation of the plan that we've seen sketched on the previous slide. Let's switch over to the terminal and see that this is indeed how PostgreSQL behaves. First off, let's re-enable again the generation of parallel plans. I had disabled this for the entire course, as I've told you, and well, these 2 statements would set the spawning of parallel workers that can contribute to the evaluation of a query back to its default value. In the default configuration of PostgreSQL, there is a maximum number of parallel workers of 8 configured. Of course, this could be changed to better suit the computing capabilities of your database host. So let's re-enable parallelization here. Okay, done that. Right. Well, then there's nothing else to do. We do not have to rewrite our queries. Parallelization is supposed to be completely transparent to the query user. We expect the query optimizer to detect opportunities for parallelization automatically. And indeed, this would be just our playground query, our probe query that we have already discussed in the previous video. Now let's look at the plan with parallelization enabled. Okay, so a bit more space to look at the plan here. All right. Okay, so indeed we start with a parallel sequential scan here. All right. You see that there is this parallel sequential scan that has been planned. You see this indicator with loops equals to 3. This indeed indicates that three workers are indeed contributing to this parallel sequential scan. The leader itself plus 2 workers, worker 0 and worker 1. All of these are contributing to the parallel sequential scan. All of these have been assigned their partition of rows in the group table to operate on. And the size of these partitions can be seen here in this rows attribute in the plan. So these are 310,000 rows, 350,000 rows, and well, okay. And indeed, the exact third of 1 million rows, 333,333. Oh my God. All right. So if you add all of these row counts together, then this should add up to 1 million. So all of the rows, of course, are processed, but all of the workers share the load almost evenly. Okay. So this would be the parallel sequential scan, which would feed their output into partial hash aggregation. So of course, all of the workers, the 2 workers that have been spawned, and also the leader, they are contributing to partial hash aggregation. We will build 3 separate hash tables in the leader and the 2 workers. And as you can see, the number of entries in this hash table are indeed 10,000 in the leader as well in all of the workers. This is an indication that indeed each worker contributes to all of the groups that are being constructed here. If you recall, our query here, our playground query will indeed create 10,000 groups. All of the workers contribute to all of the groups. So indeed, there is some work left to be done in the finalization. All of these partial aggregates that we are computing in these 10,000 groups have still to be collected together and then added up to yield the final sum aggregate, the global sum aggregate. All right, so this is the partial hash aggregates. Their results would then be gathered together. So 10,000 entries contributed by each of the workers, 10,000 entries contributed by the leader leads to 30,000 entries that have to be gathered all together. All right, so what we received there are indeed only partial sums. Okay, so the system, of course, is aware that these are not the global finalized sum aggregate values. These are partial sums that have to be still added together. What you can also see is that the gather node is in some sense the root node of parallelism in this query plan. Everything below the gather node is indeed evaluated in parallel. So below the gather node, we find information about the worker 0, worker 1, and of course also of the leader. We can see that indeed 2 workers have been launched, and we've planned to do that. So all of the workers that we planned for could indeed be launched. Above the gather node, there is sequential evaluation again. Okay, so once we've gathered all these partial hash tables together, what we then do is finalization. So adding up the entries of the partial sums that belong together, what we will end up is a global sum, which is then also the final result of the query, which indeed only contains 10,000 rows. All right. Okay, so that would be our first parallel plan. It indeed follows the sketch that we have seen here on the slides. To be able to perform this kind of parallelization, of course, depends on properties of the operation, in this case of the grouping and the aggregation operation in particular, that we use in our queries. Only aggregates that lend themselves to such parallel and distributed evaluation are indeed considered for parallel evaluation. So the crucial algebraic property that any aggregate AG that we want to process in parallel has to possess is distributivity over bag union. This is exactly the operation that we use to horizontal partition our input table. All right, so if we throw together the partitions using bag union, we will get the original table again. We use bag union to symbolize the partitioning of an input table into multiple partitions. In this case, our input table has been partitioned into two partitions, X and Y, and we would expect two workers to independently operate on X and Y and perform their partial grouping and aggregation. All right. Well, if we want to perform an aggregation over the entire table, it's the same as the aggregation over this horizontal partition table with two partitions X and Y. And since this aggregation operation is indeed distributive over back union, well, we can also compute the left-hand side by this expression here on the right-hand side. On the right-hand side, we would perform the aggregation on each of the partitions separately and of course in parallel. So these two aggregation operations will happen in parallel. They will both contribute partial aggregates that we then have to finalize, and this finalization is indeed expressed here by this top level aggregate here. We would collect the partial aggregates and then collect their partial results to form one global aggregate value. All right. So many of the aggregates of the SQL language indeed exhibit this distributivity property. So if you think about it, you will find that count, sum, max, min, average, the Boolean aggregates and so on, they all can be processed in this particular way. So let's look at the sum aggregate. So this sum would be one particular concrete instance for this generic aggregate here. I'm sorry. All right, so we would start by distributing the work, partitioning the input table into two distinct partitions X and Y. All right, we would then perform partial aggregation in parallel on each of the partitions separately. What we get there are, of course, two partial sums, which we would then throw together, and then sum up to get the global sum. But if you look at this particular operation, then this is equivalent with, of course, just the addition of the partial sums. And this is what we've already discussed on the previous slides. So the finalization operation of the sum aggregate would be just addition. Each of these distributive aggregates come with their own version of a finalization operation. And we can indeed find that if we switch over to the PostgreSQL terminal. So let's do this one more time. Here we are back again. All right, so we can indeed check the system catalog of PostgreSQL to have a look at the finalization operations that are associated with the aggregates that are built into PostgreSQL. So let's do that. So here's this PG aggregate table that is maintained by PostgreSQL itself in its database catalog, in its meta level. And we can query that and also the PG type table to look for the finalization operations that are being assigned to and used with the built-in PostgreSQL or SQL aggregates. Let's do that. All right, so what we see here is a selection of the aggregate operations that are supported by PostgreSQL. You see the average operation here, summation, max, min, count, and so on. All of these indeed have the distributivity property that we have been talking about. All right. And they are indeed equipped with a combine function, all right? And this combine function is indeed the finalization operation that we have seen on the slides before. So for the sum aggregate, the combine or the finalization function is indeed PL, it's the plus operation. That would be just addition. All right, so for the max and min aggregates, it would be, well, it would be just a comparison operation. Or the operation that can identify the larger, or in this case, the smaller of two given values. For the count aggregate, it would indeed also be the plus operation, if you think about it. For all the Boolean aggregates, it would just be Boolean conjunction or disjunction, dependent on which aggregate we are indeed using here. And well, there's also the possibility to have a finalization operation for the average aggregate. And I invite you to think about how this finalization operation for the average operation would look like. One hint there, well, indeed, the values over which these average aggregates operate are pairs of numeric values. One of these entries will be the sum of all the values that have been seen in a group, and the other value will be the count of values that you've seen in a group, and from those the average is easily derived. Okay, right. Not all operations, not all aggregates that you know and that we've already used in the course of this DB2 course are indeed found here. There are some operations, some aggregates that do not have the distributivity property and that thus do not have such a finalization function. All right, so one such example of a non-distributive aggregate would be the array ag, which is an aggregation function that can collect all the members or the values inside a group and build and construct an array, an ordered array from these. You could think that maybe array concatenation, gluing arrays together, could be the finalization operation for the array aggregate, but this is not the case. As we will see, as we can discuss here, array ag indeed does not have the distributivity property, and well, we can see this quite easily here. So let's assume that this is our input table. It's just a table, a single column table of the integers 1 to 10. And well, the query is really as simple as it gets. We are just collecting all of these values inside an array of length 10. So not much going on here. Let's see whether the result looks like we expect it to look. Indeed, the array elements are found in ascending order here. That's being guaranteed by using this order by modifier, so that we are indeed computing an ordered aggregate here. So that would be the sequential, the non-parallel evaluation of our array aggregate. We could now think about distributing the work and partitioning the input here, partitioning the input, for example, into the even and into the odd x values, aggregate them in separation, and then later use array concatenation to throw everything together into one pot. This is expressed by this SQL query here. Let me enlarge this a bit. Okay, so that would be the SQL expression that corresponds with the parallel partitioned evaluation of our array ag query above. We would of course operate over the same input in both partitions, but well, one partition would only consider the even, and one partition would only consider the odd x values. So work is indeed distributed. Right. In each of the partitions, we would compute partial aggregates. So we would construct partial arrays here, and then finalize the entire computation by using this array concatenation to then build a global array of 10 entries again. So, but if we evaluate that, which should come as no surprise, this is not the result that we have seen above. So of course, one of the workers contributed its partial array aggregate here. The other worker contributed its array, and well, array concatenation, which just happened at this particular point, will lead to this global result, which is not the same as this. Order is, of course, significant in such array computations. So this is a different order of elements. Array concatenation alone could not be the finalization operation in this array aggregate case. We would probably need some sort of merge operation that would lead to the desired result. And indeed, if you look at a version of our probe query that is not using summation, the distributive summation, but is using the non-distributive array agg here, everything else is unchanged, and of course parallelism is still enabled in PostgreSQL, then you will see that, well, the system cannot make use of parallel evaluation, and we will see sequential evaluation as usual. All right, so indeed this is a single sequential scan, and the grouping in this case is being performed by using an external merge sort based on the grouping criterion G. All of this we have already seen, and then there is a single group aggregate node that will compute the global array agg. All right, so there's some opportunity for parallel evaluation of aggregates and groupings, but of course the algebraic properties of the involved aggregate functions have to be just right. All right, so much for the parallel evaluation of grouping and aggregation. There's a bit more to be said regarding sorting and grouping in MonetDB, and this will then be the final bit that we discuss in chapter 11, but this is something that I postponed to the upcoming video. I hope to see you there. Bye bye.